Hello everyone, welcome to the first Math Club talk of this semester. Today with us we have Hrishik Koley, who is a BMath alumni and is joining CMI this year for his masters. His interests are in combinatorics, and today he is going to give a talk on a happy ending. Over to you.
Okay, hi guys, I'm Hrishik. I tried to be a bit funny with the title, but yeah, this is basically based on a problem called the happy ending problem. The name was coined by Paul Erdős because there were two people, Erdős-Szekeres and Esther Klein, who were working on this problem and got married while doing it. So Erdős coined this name. But yeah, off to more important topics. So just bear with me for the first few minutes. I'll go through some basic definitions and then we can get into the better stuff. So set C belonging to the 2D plane is convex if whenever x comma y belonging to C, the whole segment of x and y lies in C. A quick example, consider any 2 points and then you will see that any line through them lies within this, like consider any of these 6 points lying on the outskirts. So join any of these 2 lines and 2 points and you will see the line lies exactly within this polygon. And there's something called a convex hull. You might remember it, might not very important. Just for the sake of the definition, I'm giving it. So for P, a set P1 through Pm, the convex hull of P is basically the summation of all the linear combinations of all of these points, where the summation of all the scalars that you use in the linear combination is exactly 1. So that is the smallest convex set containing this set of points P, or the convex hull of P. Moving on, this is something that I will use as a terminology, which I'll call the convex position. So basically, any point that lies on the boundary of the convex hull, we call it the convex position. So for example, all of the 6 points here that you see are in the convex position because they all lie in the boundary. But the orange point here, that lies inside, so it's not in a convex position. Now coming to the important question. So, okay, maybe we could keep this a bit interactive if you all would like. So how many points do you think we need to create a k-gon on a 2D plane? Well, you need another assumption that the points are not collinear, right? Because you cannot. So yeah, that's our first assumption that we go by, is that, I mean, the answer could be infinitely many points if all of them are collinear. So you assume that no set of 3 points are collinear. And then under this assumption, you always know that k vertices are enough to form a k-gon. A quick example of that. Now here what you see is, okay, if anyone does not understand what convexity is or anything, just think of this as well, what a convex polygon is. Just think of this, that every end that it has, like every vertex is a pointed end. Like it does not have this kind of a thing. So you do not have this, something pointing inwards. All of the vertices point outwards. Or all of the edges meeting at a vertex point outwards, rather. So yeah, so with 3 points, you can create a trigon, or rather even more generally a convex trigon. But what about 4 points? You can create a quadrilateral always. Both of these are quadrilaterals. But you see, one of them is a convex quadrilateral and the other is not. So how many points do you think we need to create a convex quadrilateral? Yeah, so you need 5 points. And so this kind of seems like a very degenerate question as to how many points you need to create a k-gon. Rather, we add some more specificity to it and we ask how many points do we need to create a convex k-gon. And that is what the happy ending problem asks. How many non-collinear points do you need to create a convex k-gon? Well, let me mention this, that by non-collinear, so I don't want to say every time that every set of 3 points is non-collinear. So whenever I say non-collinear points, I mean that no pair of 3 points is collinear. So and it's represented by a function that's written as es of k. That's called the Erdős-Szekeres function. That is an extremal function. That is the least integer. Yeah. So the Erdős-Szekeres function is the least integer m, such that every set of m non-collinear points in the plane contains k points in convex position. So, as Joshua, right? Yeah. So as Joshua said, you need 5 points to roughly create a convex polygon, or a quadrilateral rather. So check this out, that you have a triangle and you have a point inside it. You cannot create a, as to say, a convex quadrilateral. But let's say you have 2 points. So if you have 1 point outside of this triangle, it's very easy to see that you can create a convex quadrilateral. Now consider that the other point that exists inside this triangle. Well, in that case, you can just draw a line through those 2 points and then the nearest 2 vertices of the triangles, and you can always form a convex quadrilateral. So the Erdős-Szekeres function of 4 is 5. And then for a pentagon, it's 9. So then I need to do a lot of case bashing to prove that whether it's 9. So I'll just, this is a picture that could potentially show you that how 8 points can never form, like there's a case where 8 points do not form a convex pentagon. We can take a quick look at this. I'll wait for 10 seconds and then we'll move on. And if you are convinced or otherwise. Cool. So as it turns out, you know the Erdős-Szekeres function value for 3, 4, 5, and 6. And all of them coincide with 2 to the power k minus 2 plus 1. And that's what Erdős-Szekeres conjectures, or it's named the Erdős-Szekeres conjecture, is that the value of this Erdős-Szekeres function is always 2 to the power k minus 2 plus 1 for k. The interesting part is that from k equals 7 onwards, you know nothing of what the Erdős-Szekeres function value will take. You know upper bounds, you know lower bounds, but no exact formula for it per se, or exact number. Even the case of k equals 6 was a computer-generated proof and was not possible for humans to do by hand. Moving on. So now time for me to convince you that the Erdős-Szekeres function always takes a finite value. Because you might ask that, okay, for a very large number, it may turn out that there are never finitely many points that you can take such that it forms a convex k-gon for large enough k. So that's what the Erdős-Szekeres theorem states. Note this is different from the Erdős-Szekeres monotone subsequence theorem. So yeah, the theorem states that for every positive integer n, every sufficiently large finite set of points in the plane in general contains a subset of n points that form the vertices of a convex polygon. So I'll take a quick detour and I'll try to prove this in 2 ways. One is basically using a geometric analog of the Erdős-Szekeres monotone subsequence theorem, and the other is using a hypergraph analog of a... Okay, do you guys know what Ramsey numbers are? Anyone who does not know? Okay, cool, I'll come to that then. Anyone knows who Erdős-Szekeres theorem is? Or does not know, rather? That's a better question. Does not... Oh, cool. So yeah, so the Erdős-Szekeres theorem states that monotone subsequence theorem states that for every rs plus 1 distinct real numbers, it either contains an increasing subsequence of length r plus 1 or a decreasing subsequence of length s plus 1. The more degenerate case is that setting r and s to be equal to n, every n square plus 1 distinct numbers force a monotone subsequence of length n plus 1. Is more of a thing whose geometric analog will be giving. N square plus 1 distinct numbers force a monotone subsequence of length n plus 1. So now for the proof of this, or rather a proof idea, you can go over the rigorous parts yourself. So take I sub I to be the length of the longest increasing subsequence ending at some ai, where, okay, this down. So a is A is a set of some rs plus 1 many numbers, and then ii is the, or maybe I'll not write this. That's written over there. Yeah. So ii is the length of the longest increasing subsequence ending at ai for any of this ai that you choose from A. And di is the length of the longest decreasing subsequence ending at ai, again choosing from here. Now what you do is assign a label. So consider the label as a function. And then the label function assigns to ai these two values, capital I sub I and capital D sub I. So now assume that there are no increasing r plus 1 subsequence and no decreasing typo, no decreasing s plus 1 subsequence. Then the largest increasing subsequence would lie roughly between 1 and r, and the largest decreasing subsequence will lie between 1 and s. So in that case, there are only rs many different labels possible. Clear? Because there are many different longest increasing labels and s many longest decreasing labels. So you have broadly rs many different levels. Now what you do is you case bash a bit. Take some I and j, I strictly less than j, and both belonging to the interval 1 and rs plus 1. Now append a. So if for I strictly less than j, you have that ai is less than aj, then append aj to the longest increasing subsequence that ends at ai. Since since for every ai you have a longest increasing subsequence that you represent by capital II, so this new ij that you have after appending aj to the end of this longest increasing subsequence, it must have length strictly greater than I sub I plus 1. And if it's the opposite, that ai is greater than aj, then you append aj to the longest decreasing subsequence ending at ai. So again, d sub j is greater than equals d sub I plus 1. So now you can convince yourself from this that no two labels can be same when I and j are not equal. So the label function is an injective function. And now you see that we have rs plus 1 many elements here, and you only have rs many possibly available labels. So simple pigeonhole principle, that at least two of them must share a label, which gives the contradiction. And yeah, so that gives us a contradiction, and then you can convince yourself that our assumption that there exists no increasing r plus 1 subsequence or no decreasing s plus 1 subsequence is false, and you have a proof for this by contradiction. Now, okay, question to you guys. Do you think we can apply this idea directly to prove that this Erdős-Szekeres function has always a finite value? Let me give you a hint. Consider, so you have geometric points there. So consider their slopes. And can you do something with those slopes, maybe an increasing subsequence, a decreasing subsequence, or whatever, to get a convex polygon in finitely many points? Yes or no? Hands up for yes. Cool. So it's no for the other. Okay, see, there's a very, very small problem that can be quickly fixed. The thing is, what Erdős-Szekeres monotone subsequence theorem says is that for r plus 1 distinct real numbers contains either an increasing subsequence or a decreasing subsequence. Apply the same thing to the slopes, but what happens then is basically so how do you define slopes? It's between any 2 points. Say you have p1 through n many points. So a slope can be p1, p2, then p3, p4, p5, p6. You see that these slopes might not be belonging to 2 consecutive edges. So sure, you get an increasing subsequence or a decreasing subsequence, but not a convex polygon per se. So what we then do is use try to give a geometric analog of this theorem. And that is what we call, so that is how we define slope, basic 11-12 stuff. So now what you do is basically take all the points on the 2D plane, arrange them based on their x coordinates that we do there, x of p1 through x of pm. Now for any 3 consecutive selected points, define this thing called turn, which takes 3 of these points. So if the value of turn is greater than 0 if the slope of pi comma pj is less than pj comma pk, and vice versa. It's less than 0 if the slope of pi comma pj is greater than the slope of pj comma pk. We use this idea to yeah. What is the slope is? So, I mean, then that's the largest slope, right? I mean, you can define a greater than or less than relation on that. I mean, see, if you have 2 perpendicular lines, that does not make sense because it's just this, and that's not really a convex thing. Huh? Do?
Perpendicular slope wouldn't really be a problem. We can always reorient that entire space and so that
Yeah.
So geometrically speaking, we just consider the values and the
No. So the thing is that it's not just about 2 perpendicular slopes. It's about 2 consecutive slopes having 2 consecutive edges having the same slope. You can't think of this as like these 2 are more or less like one edge rather than 2 different edges. So you take a strict, so that's why there's no less than equals or greater than equal sign. It's strictly increasing or strictly decreasing. So a more formal way to define turn would be the determinant of bx minus ax, by minus ay, cx minus ax, cy minus ay. I won't be proving this. This is for you all to convince yourselves. So yeah, just like even without the slope, there's a much more easier way to think of this. The turn of any 3 given points, if it takes a left turn per se, then you say that the turn has value greater than 0 and it's less than 0 if it takes a right turn. So, and also we had the non-collinearity condition, so the turn cannot be 0, so these 2 can't be equal. So we started off with the condition of non-collinearity. Now, you order the points by the x coordinate, and then if the turn is greater than 0, you will have this kind, like for many points to come by, which are joined to each other, then you will find this kind of a shape. Not the best convex polygon you can do, but a convex polygon nonetheless. So, like, you have 2 specific options in this case. If you have a sequence of points which are joined to one another and the slope strictly increases, then you form this kind of a shape, which we will call a cup. I'm removing this for now. And if you have consecutive vertices which form a decreasing sequence of slope, then you form this thing called a cap. You get a cup or a cap, and then you just join the first and the last vertices, and you have a convex polygon. So for the formal definition, a k cap is basically when the slope of p1 comma p2 up till pk minus 1 comma pk is a increasing sequence, and a k cap is the exact opposite. Example. So now, oh yeah, so I already mentioned this too, that when you have this, you just join the lines and you get a convex polygon. So now the upper bound part. So I mean, I think you all will get this, that if you can give an upper bound on any function, then it means that it is finite. So let f r comma s be the least integer m such that every m point set in this non-collinear arrangement contains an r cup or an s cap. Our goal is to prove that f r comma s is less than equals r plus s minus 4. Choose r minus 2 plus 1. And since this cap or cup thing always forms a convex k-gon, so you can say that the Erdős-Szekeres function is less than equals this fk comma k. So now we'll prove this by induction. So for the simpler cases, take a 3 cap. So if 3 points are selected, we are roughly done. There's no as such. You don't need to even think about the slope or anything. So for any so f r comma 3 is r. Are you convinced of that? Because you, so think of this, oh, sorry. Yeah, so f r comma 3 is r. So let's take the first term to represent the cup configuration and the second term to represent the cap configuration. We'll just go by that. So f r comma 3 is, you either have a r cup or a 3 cap. So take it that you do not have a 3 cap. So that means there is no this kind of a thing. So everything is like this. So r many points and you are done with it. So f r comma 3 is r. Similar argument, just reverse for the other part. And these agree with the proposed formula. So the base case is done. Now we set up this recurrence to then get the bound for f r comma s. So let us consider some set of points P which contains f of r minus 1 comma s plus f of r comma s minus 1 many points. Take points out of it and form a different set L such that every point in L is the leftmost point of an r minus 1 cup. So if this is an r minus 1 cup, you take all of these points out and then put them into L. Now you have two cases. Take the set P and take all of those points out that you have in L. So if the cardinality of P set difference L is greater than equals f of r minus 1 comma s, then that means it must have r minus 1 cup or an s cap. If we have an s cap, it's fine by us because all we ever wanted for f r comma s was an s cap. But it cannot have an r minus 1 cup because all of those points that were the leftmost point of any r minus 1 cap have gone to P. Have gone to L. So getting an r minus 1 cap is impossible, but you can get an s cap. Now, so the other case would be that this P set difference L is less than f of r minus 1 comma s, which would mean that this set L has cardinality greater than equals f of r comma s minus 1. So L either contains an r cup or an s minus 1 cup. Oh, good. I wrote it down. Yeah. So consider this. Yeah. So consider this, that this L has an s minus 1 cap. I mean, if it is an r cap, we are done again because f r minus s needs to have an r cup. So the only case that we need to be worried about is s minus 1 cap. So assume you have this s minus 1 cap. Now label all of those vertices in this s minus 1 cap for q1 to qs minus 1. And because qs minus 1 is the rightmost point in L, and also for L we chose all of those vertices that are the leftmost point of an r minus 1 cap. From each of these points an r minus 1 cap starts. So you have this kind of an arrangement. So this is your s minus 1 cap that we got, the q1 through qs minus 1. And this is the r minus 1 cup, which you will obviously get because L has all of those points that are the leftmost point of a r minus 1 cup. So now you compare the slopes. Compare the two slopes that meet at qs minus 1. So basically this and this. So one case could be that this slope is less than this. In that case, so this is qs minus 2. So in that case, so if this qs minus 2, qs minus 1 slope is less than this slope qs minus 1, is this part visible? Cool. So yeah, if this slope is less than this slope, then you can just append this qs minus 2 vertex to this r minus 1 cup and you get a r cup. So you're done. But what if it's the other thing? Say qs minus 2 has slope less than qs minus 1 q1. So then what happens is you take this s minus 1 cap, append u1 to it, and you have a s cap. So no matter what happens, if you have these many vertices, f r minus 1 comma s blah blah blah, then you will always get a r cup or an s cap. That sets up our recurrence, and yeah, so same thing. And simple calculations, like take your induction hypothesis that everything works nice and dandy for anything r less than r and s. So replace fr minus 1 comma s with your formula, replace fr comma s minus 1 with the formula, apply Pascal's identity, you have your upper bound. And this then, and as does the pointer work in this? I've never. The Erdős-Szekeres function is less than fk comma k. So this also serves as an upper bound for the Erdős-Szekeres function. Yeah, so now you do not have an r and s per se, so you just take r and s to be equal, and that is the upper bound that you get for the Erdős-Szekeres function, and it has a order of big O of 4 to the power k by root k. Do you guys know what asymptotic notations are? Anyone who does not know? 1, 2, 3. Just. No, I cannot go that way. Okay, so let's say you have a function f and you have another function g. If f is in all cases less than some constant c, so fx for all x is less than some constant g multiplied some constant c multiplied by g of x, then you say that f belongs to capital O of g. Just that. And then there are different kinds of notations, like if this is a less than, then you have what is it when the less than? So if if this is a inclusive inequality, then you have this, and if it's not, then you have a small O of g. Right. So this is the greater than, this is theta 1 was theta of g. Sorry? So this was so you have all of these notations, but you broadly need to care about what the O notation is. So care about this, forget the rest. Sorry, my bad. This will be this. So this is the order of roughly 4 to the power k by root k, but unimportant stuff. But you see that these quickly give very large number of bounds, like check for k equals 10 and it's already very large. So not a very good bound. The next bound that I'll try to give is, okay, I'm giving it because it's a very interesting way to give a bound. It does not give anything better than this, but it's a nice tool to learn. But any bounds that are better than this are quite a bit involved. I have added some references at the end. I've also added a slide for all the progress that has happened. So, okay, maybe I'll come to that later. Yeah. So, okay, I forgot. Who all does not know what Ramsey numbers are? Great. So consider you have a graph on M many vertices, and you start coloring each of the edges in that graph. Like consider a complete graph on M many vertices, and you start coloring every edge on that graph. So you say that M is the Ramsey number of n comma n. So you use two colors basically, red and blue. So you say that M is the Ramsey number of n comma n. If you can either get a red n-gon or a red blue-gon, these can be different too, like k comma l, let's say. So you get a blue k-gon or a red l-gon. So then you say that, and if it can be achieved by m numbers and it's the smallest that can do it, then you say that the m is the Ramsey number k comma l. So what is Ramsey for triples? Should I? Wait, maybe I'll do something else too. Let me convince you of these. For those who do not know, quick thing that you could try out, try proving that you will always have a red 3-gon or a red blue-gon if you have a complete 6 graph. It's a very easy proof. You can either try it out or you can check it out. Nice exercise to do. So yeah, what is the Ramsey for triples? And it turns out Ramsey for triples is basically a generalization of this shifting from graphs to hypergraphs. Again, people who do not know hypergraphs. Oh, that's true. Okay, cool. So hypergraph is basically a slight shift from a graph. So in a graph, every pair of edge is basically two vertices. So consider here. So any v1 comma v2 belongs to the edge set. This is your, by definition, an edge. So hypergraph, the idea of vertices remains the same. You have quite a few vertices. I denoted by v of, or I'll use h for hypergraphs. Yeah, so v of h denotes the vertices of a hypergraph, same definition as graphs. What changes is the definition of edges. We start calling them hyperedges. Hyperedges are basically unordered tuples of all of these vertices. So it need not be necessarily two vertices that form an hyperedge. It can be anything, 4, 5, 6, 7, as long as it's finitely many, you're fine with it. So quick example would be, yeah. So this is a hyper graph. So consider this vertices v1, v2, v3, v4. So you have these hyperedges. Another one, v6, v7, v8. Okay, coincidentally, it's all three vertices here, but yeah, you can have more than that. So yeah, this is a hypergraph. A vertex can belong to multiple hyperedges. It's just any unordered tuple. Yeah, but okay, this was convenient because Ramsey for triples deals with hypergraphs, but not the general case. it deals with what we'll call the three regular hypergraph. So what's a three regular hypergraph? It's basically all of these hyperedges have three vertices each, no more, no less. And then a quick coloring, and that gives us an upper bound. So let me just read this out. So for every n, there exists an Ramsey triple number n comma n such that you have a convex k-gon that you can form by choosing three sets of triples, and then we use that idea basically. And so yeah, it will contain a monochromatic convex k-gon of convex n-gon of, yeah. So now for the maybe for the proof of finiteness. So we come back to this idea of turn. So if we have the turn greater than 0, then we color the hyperedge containing these three vertices red. If we have a turn less than 0, then we color all these vertices, like the hyperedge containing all these vertices, blue. And you continue doing this color, yeah. So yeah, you do the coloring based on the sign of the turn pi, pj, pk. And Ramsey's theorem for triple says that given indices I1 through In such that every triple among them has the same color, then by the geometric lemma, all of these are in convex position. So the idea is that take m equals R3 n comma n. Then if you have m many these vertices, then you can find NC three many hyperedges that are all monochromatically colored. And then using that, you can always form a convex polygon, like a convex n-gon. And that becomes an upper bound for the Erdős-Szekeres number on n. So now why, and this is like worse than the cup cap idea, but so I'll just revert back to the cup cap idea. So this is one thing that becomes a big hindrance for why the cup cap idea can't give a better bound per se. Because you see, you can have a cup and a cap joining to each other, and this is neither a cap nor a cap, but a combination of both. And this is not counted for in that cup cap theorem, so you don't get a much closer bound for it. So yeah, I already stated the conjecture. And Erdős-Szekeres constructed for every k a set of 2 to the power k minus 2 non-collinear points with no k points in convex position. So this is a standard thing that holds, that the Erdős-Szekeres number is greater than equals to the power k minus 2 plus 1. So this is already tight. The tightness is missing in the general upper bound. So that's the Erdős-Szekeres upper bound. These are more recent results, like, and now I hope you guys remember what big O is. So these are better bounds that have been done in the recent years. Okay, I'll come to that later. So now another progress that I came to know of after I completed making these slides. So last year in 2025, so I have not read the paper, so don't ask me about how the things work, but it's just a general exposition for you guys. Maybe you can read it. I have referenced it. So yeah, if you are to characterize a convex polygon formed by a combination of cup and caps, then you would say that for let's say this is an S minus 1, S cap, and this is, let's say, an R cup. So characterization would be that the rightmost point of, or the end point of the S cap becomes the starting position for an R cap, and the end point of the R cap becomes the starting point of the R cap. Both must necessarily hold for you to get a combination of an S cap and an R cup forming a convex polygon. So yeah, we still do not know if when this will be proved, or even if it can be proved or not. But what I think I forgot his name. Yeah. Oh, his name was some Bake or something. I don't know. Maybe I'll show you. Yeah. So what he did is basically he proved this for a split K-gon. That is, so you have two conditions that the, okay, I represent the endpoint of a cap by this E of S and the start point by, say, this T of R. So E denotes endpoint, T denotes start point. So you necessarily need to have E of S equals T of R and T of S equals E of R. Both of those need to hold true for you to get a convex polygon. What they did is they proved that this conjectured value holds true for what they called a split K-gon. What's a split K-gon is basically you relax these conditions a bit and you say that, okay, only one of them needs to hold true, not both of them. So that was the most recent progress that has been done in this case. And then I would ideally assume, since you all are in BMath, then you'll be going on for research in further years. So yeah, maybe if you get interested in graph theory or combinatorics, these are some hot research questions that have been asked in this particular topic. I'll share the slides and you can look at them there. And these are my references. So this is the paper that dealt with the split K-gon part. And this is what deals with the, like, this is a paper you can read if you want to look into more about the Ramsey theorem for this hypergraphs. And I think that's all. Any questions, I think? Yeah, please. I'll start from there and come to you.
So when you were just saying that we were talking about the split polygon case, like this classic sequence, are you like doing a map, like you're mapping a sequence to the S cup and the R cap? Are you doing that, but that's why you're writing those two functions, like the end point and the starting point?
Yeah, I'm not writing them as functions. They are just like for identification purposes. They are just characterizations per se. That we used arguments like the leftmost points, rightmost points. So that's like more formal way of writing those things. So basically, so when you we did those longest increasing slope idea that ends at A1, or longest increasing decreasing slope idea that ends at some point. So it's basically the same idea that this denotes the point where this longest decreasing slope ends, and this denotes the point where this longest increasing slope starts. You can define it as a function if you want, but here I was not meaning to define it as a function. Yeah.
Have we defined some functions to find the Ramsey numbers of simple graphs, not hypergraphs?
Define some functions in the sense.
So, for example, we know that R of 3 comma 3 is 6. Right? So do we know that for general values, any I?
No, we don't. I think, maybe I'll state this. Erdős had this famous quote that if someday aliens were to attack Earth, then if they asked us to calculate the Ramsey number for 5,5, you would use all the computers in the world. And if it's 6,6, then you'd better fight the aliens than solve it.
So we only have the upper bound for them.
Yeah. So I think so it was 3 years back, but it got published, I think, yesterday or day before yesterday. So this was a recent upper bound by this guy named Julian Sehestra-Buddhi. So this was a paper that came out in Annals of Mathematics, I think 1 or 2 days back. So this is the best known bound that you know as of now. Nothing better than this.
General bound.
Yeah, and epsilon has some 0.0252 kind of value, so pretty small. Yeah.
So if that's the situation in simple graphs with normal edges, how do we study hypergraphs with hyper edges? Because they then have even
Yeah.
complicated edges as a set of 3 points.
So that's why there are no known values for the hypergraphs yet. All you know is that they are finite. That's it.
Also, it's proven that it's fine.
Yeah. There are finiteness results, but there are no proper like upper bounds, lower bounds as of now. Any other questions? Yep.
Why that instead of taking normal graphs, why we put hypergraphs? Why the problem?
Well, because in case of normal graphs, like for Ramsey numbers, it deals with a polygon. That's fine. But well, you had to add something? Yeah, so in the case of complete graphs, they deal with a polygon. So they are always happy if they get a, let's say, quadrilateral, pentagon, hexagon, but they do not care about the convexity part. So what the hypergraph or the three regular hypergraph does is basically it forces that convexity condition. Because to get that convexity condition, you need to define those terms per se. So that's why we took the.
There's a similar
Yeah.
recursion for Ramsey number. The FK. There is some recursion of f r comma s less than or equal to f r minus 1 s plus f r minus x minus 1.
Yeah, Ramsey has some like.
Yeah.
I don't remember.
I remember something n plus m equal to even with the.
Maybe I don't remember it. Maybe I think it had some this recurrence type upper bound, but I do not remember what it was. Yeah.
So I asked whether it has any relation.
Yeah. Okay. Any other questions? Yeah.
In the questions that in the slide that you had like future questions for research, like for the number that you had for 6, seems a pretty small number.
Yeah.
Why not let computer simulations do it? Like why?
Well, 6 was the one that computers did. It was in I think 2019 maybe, if I remember.
So difficult to
2006.
Huh? Sorry.
2006. There's a paper. 17 point.
Oh, sorry. Yeah. So 2019 was. Oh, maybe it was another solution then. Yeah. Whatever. So yes, the thing is, you consider a polygon, and then you need to consider every position that you can put that point on, and like there are like for triangles, consider this. I'm just talking about triangles for now. Yep. So now these are your 3 points. The fourth point can go into 1, 2, 3, 4, 5, 6, 7 different positions, and it increases quite rapidly for the higher values. So even in case of 4, you have quite a few positions to check. Go to 7 and you have even more. So yeah, maybe computers can do it now that AI is there, but I don't think anybody tried recently. Yeah, any other questions? Cool. No.
So no one has any other questions? So we would like to thank the speaker then, I guess. So before you guys leave for this afternoon, here's something I want to say. So Hrishik has been associated with the math club for quite as long as he has been in ISI, throughout his BMath and throughout his MMath as well. And he has been quite pivotal in the rejuvenation of the math club in its very like glorious years, so as to say. If you go to the math club GitHub website, he was one of the 2 people who made the website. Basically, he designed it from scratch. He had a funny story where he was designing the website while he was sitting in the airport and waiting for his flight. So it's quite a funny incident, but like he has done a lot for the math club, and I hope that we will be able to continue their legacy and what our seniors have taught us, the kind of quality of talks that we have received from our seniors. And so yeah, let's just thank the speakers then.